Hello, I'm John Park from Northeastern University, and I'll present modeling dynamics over meshes with gauge equivariant nonlinear message passing in collaboration with Lawson Wong and Robin Walters. Non-Euclidean manifolds embedded in 3D space naturally occur in many domains, ranging from 3D object modeling to structural biology, neuroscience, and climate modeling. Such manifolds are often discretized into meshes for computational tractability. While there exist other 3D representations such as point clouds or voxels, in contrast, meshes encode both the geometry and topology of the surface. Meshes are commonly used as only they can directly represent the manifold structure. Partial differential equations, or PDEs, govern the underlying dynamics of many fundamental problems in engineering and science. In particular, modeling PDEs over surfaces is an important task in thermodynamics, aerodynamics, acoustics, and material science. Many machine learning approaches to learn signals over meshes often treat the mesh as a graph and approximate patches of the mesh to be Euclidean. Early approaches used orientation-independent features on such patches, losing important geometric information, or chose a fixed reference frame, which may be ambiguous for some manifolds. Previous works have shown that not incorporating the intrinsic geometry of the mesh often leads to reduced performance. To properly express the geometric information of a manifold, one must consider an important symmetry of the manifold. In the left figure of the mesh, we focus on vertex B and its neighbors and project them onto the tangent plane at vertex B. There is clear ambiguity in the choice of local reference, or gauge. For example, if we choose vertex A as the reference neighbor, we get one set of orientations, as shown in the top right figure, whereas if we choose vertex D as the gauge, we get different values, as given by the bottom right figure. As the network outputs should be independent of the arbitrary choice of gauge, the network should incorporate the symmetry and be equivariant to local gauge transformations. In this work, we focus on gauge equivariant neural networks. Although previous work on gauge equivariant networks for meshes considered convolutional and attentional architectures, we find that they underperform when modeling complex dynamics. We introduce a new architecture, Hermes, that combines gauge equivariance with nonlinear message passing. Analogously to how there are largely three flavors of message passing in graph neural networks, Hermes complements previous approaches and completes the full picture. Here we show an instantiation of Hermes for one of the surface PDE datasets. A key point to note is that we effectively decouple the effect of the network depth with the receptive field of the graph. As Hermes can compute messages using features from nodes that are an arbitrary hop distance away from the source node, we hypothesize that this decoupling is beneficial in tasks with complicated interactions. We evaluate our method on several different domains, such as surface PDEs, cloth dynamics, object interactions, and also shape correspondence. For the PDEs, we consider the heat equation, the wave equation, and the Kohn-Hilliard equation. The Kohn-Hilliard equation describes phase separation in a binary fluid mixture, and is a complex fourth-order nonlinear PDE. We also test on generalization to several scenarios, to future time steps, to unseen initial conditions, and also to unseen meshes. Our experiments show that Hermes outperforms convolutional and attentional counterparts significantly, and outperforms other graph and mesh baselines in most settings. In particular, Hermes performs the best on the test mesh datasets, where we test generalization to new meshes. This suggests that Hermes is able to better learn the true dynamics function rather than instances of the PDE, and does not overfit to specific mesh geometries. Here we visualize qualitative samples from each method when the predictions are rolled out for 50 time steps, autoregressively, given only the initial conditions. On the heat dataset, we can see that GEM-CNN diverges quickly, while EMAN and Hermes generate rollouts close to the ground truth. On Kohn-Hilliard, we see that GEM-CNN has high errors and EMAN diverges, while Hermes gives realistic rollouts. In summary, we propose a new gauge equivariant nonlinear message passing architecture. Hermes demonstrates improved performance over convolutional and attentional networks on complex dynamics. We also investigate in which situations nonlinear message passing should be preferred over simpler flavors. Some limitations of this work is that Hermes and gauge equivariant networks in general cannot scale well to large meshes, and there are more design parameters to choose for Hermes. We could also consider more complicated dynamics using real-world data. Thank you for listening, and please come by and check out our poster.